Word 2vec encodes every word as a vector in 300-dimensional space. King minus man plus woman approximately equals queen. That arithmetic only works because the embedding space has the right structure, a vector space. Today we build that structure from the ground up: vector spaces, span, and basis. These three ideas explain why embedding dimensions matter, how attention heads partition information, and why PCA finds the directions it does. A vector space is any set closed under two operations: vector addition and scalar multiplication. Closed means the result stays in the set. 8 axioms formalize this: closure for both ops, commutativity and associativity of addition, existence of a zero vector and additive inverses, and 2 scalar distribution laws. Most important examples in ML are n for feature vectors, matrices for weight matrices, polynomial spaces for kernel methods, and infinite-dimensional function spaces for kernel PCA. 2 fundamental concepts. Span. The span of a set of vectors is all linear combinations, all vectors C1v1 plus C2v2 and so on, where coefficients range over all reals. If v1 and v2 are not parallel, their span is all of R2. If parallel, their span is just a line. Linear independence. A set is independent if the only way to combine them to get 0 is all coefficients equal to 0. Test in NumPy. Form matrix A with vectors as columns and compute matrix _rank. If rank equals the count, they are independent. In ML, dependent features are redundant rank deficiency signals multicollinearity. A basis is a set of vectors that is both linearly independent and spans the space, the minimum set to reach everything. Every vector has a unique coordinate representation in a given basis. The standard basis for Rn is the identity matrix columns. An orthonormal basis has mutually perpendicular unit vectors. Q transpose times Q equals the identity. QR decomposition finds an orthonormal basis for the column space of any matrix. Change of basis. V new equals B inverse times V old. Dimension is the number of vectors in any basis invariant. Rank equals the dimension of the column space. 4 applications. 1. Word embeddings. The embedding matrix maps vocabulary to RD. Semantic relationships become geometric directions. 2. Transformer attention. Each head projects tokens into a different learned subspace of D-model dimensional space. Multi-head attention decomposes the full space into parallel subspaces. 3. PCA finds an orthonormal basis for the data subspace maximizing variance. Top K projection means working in a k-dimensional subspace. 4. Device monitoring. The rank of the metric matrix reveals how many independent failure modes exist. 3 definitions. Cold. Vector space, closed under addition and scalar multiply, 8 axioms. Span, all linear combinations of a set. Basis, linearly independent and spans 2 conditions. Exercise 1. V1 equals 1, 2, and V2 equals 2, 4. Compute rank. They are dependent, span only a line. Add V3 equals 0, 1. Rank increases to 2, span becomes all of R2. Exercise 2. QR of a random 3 by 3 matrix. Verify Q transpose times Q equals identity and confirm column dimension. Vector spaces, span, and basis are the grammar underneath every embedding, every attention mechanism, and every dimensionality reduction technique. You now understand why 300 dimensions in Word 2vec is a design choice about the space you want to learn in. Video 17 connects this to linear transformations. Every matrix is a map between two vector spaces. Subscribe so video 17 is ready. Post your two basis conditions in the comments. See you in video 17.